Hi everyone, we are Group 5 with 3 members as you see on the screen, including Hu Don, Kai Dung, Hoang Phuk. Welcome to our presentation. Looking at the sky, have you ever wondered why there are some blinking dots that always stay at one position days and nights above your head and never go away? Or why does a satellite keep orbiting the Earth and never fly away? In this presentation, we will not only discuss the physics of orbiting satellites, including the forces that keep them in orbit, the different types of satellites, and their uses to you, but also use math and physics concepts to prove that what we said is correct. In addition, a detailed 3D simulation of the orbiting satellite around the Earth will also be introduced so you can have a new perspective of observing orbiting satellites. There are many types of satellites that would take hours just to introduce each of them to you. To make it easy, we would divide them into 2 categories. The first one is natural satellites. So what are they? We could simply say that they are objects that orbit around another bigger object and they are not man-made. For instance, the Moon is a natural satellite of the Earth. The second one, and also the one that we will focus on today, is artificial satellites. To make it easy at first, you can simply understand that they are anything that is man-made and orbiting. And in this video, we will focus artificial satellites that orbits our planet Earth. We will have 3 main sections of this video. The first one is the introduction to 3 types of artificial satellites, including geostationary, geosynchronous, and polar satellites. Next, we will focus on the physical concept of the satellites in the second section. We will explain to you how they orbit around the Earth using physics and mathematics. And finally, we will show you some examples and simulation of the satellites to help you visualize the way they work. So, let's begin with geostationary satellites. We will call it GeoSat for short. Let's imagine this is the Earth, and the place here with the flag, or Vietnam, is where the GeoSat was intended to be located. Then when a person in this location observes the sky using a telescope or even naked eyes, they would easily notice the satellite orbiting above them. However, the interesting fact about this satellite is that it will always be at the same location in the sky forever. The reason is that the time it takes for the Earth to complete one rotation around its own axis is the same as that of this GeoSat. Therefore, the satellite seems to stay constantly at one location in the sky. The geostationary satellites move on circular paths whose projections are parallel to the equator. They move at the same time as the Earth finishes a revolution about its axis, 2393h. Therefore, those satellites have the same angular velocity as the Earth. Let's take a look at this interesting demonstration of a satellite orbiting around the Earth. To understand the concept, you first need to know that the Earth is rotating on its axis at a rate of 15 degrees per hour. This means that the Earth rotates once every 24 hours. Second, the satellite in geostationary orbit is orbiting the Earth at the same rate as the Earth is rotating. This means that the satellite is always moving at the same speed as the Earth's surface. Third, the satellite is orbiting the Earth at the same altitude as the Earth's equator. This means that the satellite is always above the same point on the Earth's surface. The combination of these factors means that a satellite in geostationary orbit appears to stay in the same place in the sky, relative to the Earth's surface. In this simulation, it is Earth-centered, which means the perspective is fixed on one side of the Earth. By doing this, we can demonstrate that the GeoSat stays above one location on the Earth all the time. 1. This view is to show the rotation of the Earth and the orbit of the satellite. You could see that the period of the satellite orbiting around the Earth matches that of the Earth rotating around its own axis. Alright, we have talked about the GeoSat in the previous section. However, we are going to talk about the general case of the GeoSat, the geosynchronous satellites. So why it is called geosynchronous? The word sounds so comprehensive. Let's break it down into 2 parts, geo and synchronous. The prefix geo means that it is related to the Earth, and the word synchronous means having the same period. We can simply say that the period of the Earth and the satellite are synced together. Now, let's take the previous example into consideration. The location is Vietnam. The case here is one person observing the motion of the satellite using a telescope. Let's imagine a camera is used for tracking the motion of the satellite, and this will be the pattern of the trace of the satellite. The shape of the number 8. In general, a geosynchronous satellite is a satellite that orbits the Earth at a distance of 35,786 kilometers above the equator. This distance is called geosynchronous orbit. So, the geostationary is a special case of the geosynchronous satellite. In this demonstration, we show you the orbit radius of the 2 satellites. From the demonstration, we can see that the geostationary satellite is the case when the incline between the equator and the radius of the satellite is 0 degrees. Because the physical concept of the geosynchronous and the geostationary satellite are the same with the difference being just the incline, we would show you the different traces each satellite leaves on the Earth's surface. Now let's talk about polar satellites. They are satellites that orbit around the poles of the Earth, which make the angle that it spins almost 90 degrees compared to a geostationary satellite. There exist many polar satellites, and the majority of polar satellites orbit in low Earth orbit, which is below 2,000 kilometers from Earth's surface, above 2,000 kilometers, and below 35,786 km is where the geostationary and geosynchronous orbits, and above that will be the high Earth orbit. So next up, we're going to discuss how a satellite went from the surface of the Earth to its orbit. Usually, when launching a satellite into its orbit, the satellite usually hitches a ride on a rocket or on the space shuttle, where they are placed inside the cargo bay. Let's say when launching the rocket contains both the mass of the rocket itself and the fuel to power the rocket, which we will call m with an initial velocity. Put the system into a y-x scale, we can see that the instantaneous velocity of the rocket will be v times vector I. Thus its initial momentum will be p times mvi. The burning gas during the launch will be ejected in the x direction. During a small amount of time dt, the mass of gas being released will be dmg, which will leave with a velocity of u. As a result of the burning fuel pushing the rocket, the mass of the rocket will be missing the mass of the gas in a small amount of time, m minus dmg, and the instantaneous velocity will increase by an amount of dv. Although the rocket velocity dv is measured with respect to Earth, the exhaust gas velocity is measured with respect to the moving rocket. Measured with respect to the Earth, therefore, the exhaust gas has velocity v minus u. This will be all put together to find the final momentum of the rocket. Using the conservation of momentum, we have the initial momentum will be equal to the final momentum of the rocket, thus we can calculate. Since dmg times dv are arbitrarily small, we can neglect those values, and since that dmg is the amount of gas being burned and ejected, it will be also equivalent to the small amount of gas being reduced in the total mass of the rocket. We have the final equation. Final velocity minus initial velocity equals to u times the natural log of the initial mass over the final mass. Now let's move on to orbital components. The law associated with any object moving in a circle or along a curved path applies to satellites. The velocity of the satellite is directed tangent to the circle at every point along its path, and the acceleration is directed towards the center of the circle towards the Earth. This acceleration is caused by a net force that is directed inwards in the same direction as the acceleration. Gravity alone influences the satellite's trajectory, so it always falls below its straight line, inertial path. This is depicted in the diagram below. Now, let's have a deeper dive into the calculations. The net force between the satellite and the Earth is g times the mass of the satellite and the mass of the Earth divided by r squared. With net force equals ma, we can cancel out the mass of the Earth, and the equation will be as follows. An orbiting satellite having a mass of m satellite experience a net force of mv squared over r squared. This net force is supplied by gravity and given by the expression F net equals g times the mass of the satellite and the mass of the Earth divided by r squared. From that, we can derive the equation for v as the square root of g times the mass of Earth over r squared. From this equation, we can see that the speed of the satellite isn't affected by its mass. If the planet's mass increases, the orbital speed will increase. If the orbital radius decrease, the orbital speed will increase. But if changed in satellite mass, v will have no effects. And considering that the period of rotation, t, equals 2 pi over v, substituting v will give us the orbital period of the satellite. So in summary, we have these equations that we have to focus on. Now let's change back to our final part, which is applications. Geostationary satellites can be used for tracking volcanic ash and measuring cloud top temperatures. Another use is oceanography, which is the scientific study of oceans. Last is communication, like VIN-SAT. Geosynchronous satellite is used for weather forecasting and television broadcasting. Other useful application of geosynchronous satellite is remote sensing and GPS. Polar satellites also have many applications. It is used for mapping and surveying, and most important of all, communication satellite for countries or areas near the poles. So that concludes our presentation about orbital satellites. Thank you for listening, and if you have any questions, feel free to ask us.